Okay, so for the next session of this morning, it's my pleasure to introduce Stephen Dolan, who is going to talk about OCaml and Rust.
Thank you. So, I like to program in safe languages. Safety means that anything the language accepts as a program, it tells you what it's going to do. So you might still have bugs in your program, it might not do the thing that you wanted, but the language spec still specifies what's going to happen. In unsafe languages, there's no specification of what's going to happen when you have a bug. If you have a bug in a C program, you have undefined behavior, you could easily have something completely, some vulnerability could be exploitable, it could start running attacker-supplied strings as code. So in safety, in a safe language, there's at least some limit on how much damage a bug can do. This is a different issue from how easy it is to use the language. Ease of use is about how easy is it to write correct programs, and safety is about what happens when you don't. For instance, C++ over the last maybe 15 years or so has made massive advances in ease of use. If you tried writing memory safe C++ in the presence of exceptions 15 years ago, it was a disaster, and these days you can use shared pointers and unique pointers and other such fun things, and it's much easier to write correct programs. But if you fail to write a correct program, the consequences are still just as bad as they used to be. You get buffer overflows and seg faults and memory corruption and vulnerabilities. So, in order to be safe, you must use memory safely, and that boils down to keeping track of the layout of memory, so what are each of these bits of memory being used to represent, and the lifetime of memory, how long are those bits of memory going to be there. So you can achieve this by a mix of static and dynamic techniques. Statically, you can have a compiler that does some analysis of the program to prove that it's never going to do anything invalid. Or, dynamically, you can have some runtime support that's checking whether the program is currently doing something invalid and stops it. And most languages adopt a mix of these two techniques to achieve safety. For instance, in C and C++, you have mostly static types for layouts. So there's structure types and so on that keep track of like the offsets of fields and so on. A bit more of that in C++ than there is in C. It's totally unsafe when you're doing indexing, so array lengths are not checked. And it's totally unsafe for lifetimes. There's no static checking that things are still in scope by the time that you use them or that memory hasn't been accessed after it's freed and so on. JavaScript, for instance, is on the very opposite end of the scale. It's a safe language, but it is completely dynamic safety checking for layout. So it's do runtime type tests to check that some things aren't being accessed in invalid ways. And it's got completely dynamic checking for lifetimes. It's got a garbage collector to check, to dynamically determine how long each lifetime must be. So the two languages I'm going to talk about are ML and Rust, which have a reasonably similar approach to safety. They both have a mix of static and dynamic checks for the safety of layouts. So they've static types to describe the layout of bits of memory, with dynamic checks for bounds checks. There's no static typing of like array indexes in either Rust or ML. But the difference is, in ML, lifetimes are checked dynamically. There's a garbage collector working out how long each object must live for, and in Rust they're checked statically. The types express how long each reference is valid for and how long each object will live. So, I would really like to be able to mix these in the same project, because, I mean, if I'm willing to put in the work, I can get really good performance and really tight control over memory limits in Rust. But honestly, I'd prefer to just be writing nice garbage collected functional code most of the time. However, mixing languages is really hard if they implement safety in different ways. Because Rust is going to expect that anytime there's a use of a pointer, its safety has been checked statically. It's going to assume that some bit of code has proven that pointers can't be accessed outside of their lifetimes. ML, on the other hand, is going to assume that there's enough runtime support that the garbage collector can understand which objects are still in use. So it's going to assume that any pointers have been registered in a place that the garbage collector can find them. So to mix these two together, we need to somehow explain to the Rust side that it needs to tell the garbage collector about any pointers that it uses, and explain the ML side that we somehow make up lifetimes for things that the garbage collector is tracking so the bus can understand them. So, the standard way of mixing two languages that's almost ubiquitous is to go everything via C. And this basically doesn't work, and I'll have a few slides describing the manner in which it fails to work. There's been various projects like C types in OCaml or inline C in Perl or Haskell FFI whatsoever, or various other ones that attempt to make going via C a bit easier, but none of them make it safe. There's some systems where it's the amount of code that you should write to do a C binding. Say if you're using Swig, is very low. But if you get your use of lifetimes wrong, then no matter how safe the language you're trying to connect to is, the result is a completely unsafe thing that will crash or corrupt memory or be exploitable if you use things outside of the lifetime. So to explain just how much of a pain it is to interact with a garbage collected language via C, we're going to talk about the OCaml FFI. So here is a function in OCaml which takes two things and constructs a pair of them. So in the C, so OCaml has a C FFI, so if we're trying to talk to C programs from OCaml, then we write some code like this. So it's the construction of the pair has been split up into parts here. There's a call to caml alloc, where we're allocating the pair. Then we're filling in the left field, filling in the right field, and returning it. And so anyone who's written any code with the OCaml FFI will probably see this and see that it has a bug. And the bug here is that the two values A and B are they're values that the garbage collector doesn't necessarily know about. So during the call to caml alloc, that might trigger the garbage collector. The garbage collector might see that there are no other references to A and B. It will collect A and B, and then they will just be full of invalid, corrupt nonsense by the time caml alloc returns. So in order to prevent this, you have to manually register these two values with the garbage collector, adding these macros that tell the garbage collector that A and B are values that the collector should know about, values that the collector should keep alive. So this is what the correct version of the code looks like. But the problem is, there is nothing except for the experienced programmer standing over your shoulder that will tell you that this is correct and the other one was wrong. Both of them will pass the C compiler with no warnings. So it's mildly annoying to have to write this, but it's much more annoying that there's nothing shouting at you when you write the wrong version. It just may or may not sync fault sometimes. So this example isn't too bad. It's when you're using values on the OCaml heap, you wrap them in this caml parameter. But it gets a lot worse. It's surprisingly tricky to get this right. I mean, I've been working on the OCaml garbage collector and working on adding multi-core support for quite a while now, and I still get this wrong on occasion. So suppose we're trying to call this pair function. So we're trying to create a triplet or a pair of x, and for the second component is a pair of x in itself. So naively we might imagine that that's a reasonable bit of code to write. But can anyone see that there is a problem with this? So the issue is, during the call to pair, the value x is not being registered with the garbage collector. So if the first call to pair triggers a collection, then x could be overwritten or moved or corrupted in various ways, and this code will site fault or crash or leak personal data or whatever it is that C programs do when you look at them sideways. So an experienced OCaml FFI programmer will realize that you need to register that variable x with the garbage collector. So now the garbage collector knows about this variable x, and it knows that if the first call to pair, by first call to pair I mean this one, the one that's actually evaluated first, if that triggers the garbage collector and x gets moved, then OCaml then knows about the variable x and will update it correctly. However, this code is still wrong. This code is wrong surprises people who've written OCaml C code for years. The issue is, in C, the order of evaluation of arguments is not well defined. C is perfectly within its rights, and GCC will actually do this, to evaluate the left argument to pair first. So it loads X, and it puts that in a register or in a temporary location somewhere, and then it evaluates the right-hand side, it evaluates the call to pair. The call to pair triggers the garbage collector. The garbage collector knows about the original variable X and correctly updates that. But it doesn't know about this temporary register that the compiler used to store the previously evaluated first argument. So then it returns, when that pair returns, the variable X, the variable location on the stack, has been updated properly, but the temporary that the compiler introduced has not, and it gets the wrong answer. So that is the sort of bug that I at least am not capable of finding without either a week's worth of debugging or a type checker. I do not like doing weeks worth of debugging, so I would prefer if a type checker told me about this. So I would really like not to be writing this sort of code in C anymore, because the type checker in C never tells me very much in use. Yeah, so this is what the correct version of the code looks like. So instead, I would like to talk about linking OCaml with a low-level language using camel oxide, FFI from OCaml to Rust. So here, we have more or less the same code, except it's in Rust syntax. We're allocating a pair of X and X, and then we're allocating a pair of X and this temporary second thing that we've written. And this has the same bug as the original code. There's nothing, this use here of X, there's nothing ensuring that that will still be alive by the time the garbage collector returns from this allocation from this alloc pair call. But because this is Rust and we have an actual type checker that's checking things, we can try compiling this, and it's bigger. We get told that it's talking about mutable borrows for reasons I'll explain in a moment, but it's basically saying that this call is bad because we can't use this thing at the same time. So it's detected that we can't do this call and expect this X to be available. So the fix is much the same as the fix in C. We have to add a variable the garbage collector knows about, and then access it down here. And so that compiles to more or less, that looks more or less like the correct version of the C code. This is not much of an improvement on ease of use over the CFFI. The goal here is safety. The Rust type checker is actually able to tell the difference between the code that is correct and the code that is not. It even runs the little OCaml program. This FFI is a proof of concept at the moment. It supports not very many more types other than strings and pairs and lists and so on. But here's a little bit more code that's showing off the other bits of the FFI that work. We can have functions that do some string formatting in Rust and pass the results back as a string in OCaml, or functions that construct pairs of arbitrary values, or functions that do some string manipulation. So essentially, the number of types that this FFI supports is limited to a fairly small subset of OCaml at the moment, but we can fairly easily link the OCaml and the Rust code together. Especially if we have curly brackets on that spot. Yes, here is some code about everywhere that does some things. But actually, the most interesting bit of this is not so much that we can call the functions, it's that the functions actually have OCaml types. I'm not sure if it's readable down there. So here is the signature of the module which is generated by that file of Rust code. As you can see, the definitions in Rust get translated to definitions in OCaml, and these are all type safe. If the code that you write in Rust passes the Rust borrow checker, then the things exposed to OCaml are not going to cause the garbage collector to blow up. So I'm going to talk briefly about how this is implemented. Rust has lifetime types, which Rust tracks lifetimes in the types. So there's two sorts of reference type in Rust. There are these references with some t valid for a particular lifetime, and these things with mut in them, which are references to some type t, which are valid for a lifetime and are the only reference that exists in that lifetime. So Rust calls these immutable and mutable. That the idea is that you can only have one mutable reference to a thing, but many immutable references to it. What they really mean is they're shared references and exclusive references to a value. So then, the game in this FFI is to express OCaml's garbage collector invariance in terms of Rust lifetimes. So there's a value GC. Every temporary value, anything that might be moved by the garbage collector, has a immutable reference, a shared reference to the garbage collector, and every operation that might allocate requires a immutable, a unique reference to the garbage collector. So then the Rust borrow checker verifies that any of the temporary values that might be invalidated by the garbage collector, those are never live across a point at which an allocation might be done. So in the Rust code, I left out most of the types because it's possible and further, but in the Rust code, there are three types that are interesting. There's this thing which is a reference to the garbage collector for a scope GC, which is the function that you're implementing. And it says that the GC will not run for this lifetime A. Then there's a value, which is this type, and the value only exists for this lifetime A. These are temporary values, not that the GC doesn't know about, so you have to prevent the garbage collector from running when those are alive. And then there's a variable registered with the GC, which is live for the entire scope of the function. So that was what we used in the Rust code to keep a value alive across what's called might allocate. We had an initial temporary value, and Rust gave us a compiler trying to use that across scope and call to the collector. But by converting that into a registered variable, we can use it wherever we like. So, in general, I want safe languages to have safe interfaces. If I'm mixing two safe languages in a single project, which is a very sensible thing to be doing, then the glue between them should be just as safe as the languages themselves. And two other things in this direction that are worth having a look at are Josephine by Al Jeffries recently, which is similar to this, about mixing JavaScript, the Mozilla Spider Monkey implementation, and Rust. And a paper from a while ago that was doing similar checking to OCaml CFFIs, although since it was still C, there was still some safety there. But generally, there's one thing I want to convince everyone at this talk is that if we are connecting two safe languages, we really should have a safe interface between them. Thank you.
Before we take questions, let me present you with this presentation release agreement. So.
Thanks. I'd like to
think of a very good question to ask Stephen. And oh yes, Jeremy, you also have one. Yes. So Jan.
So I'm a bit surprised by the types that you exposed on the Rust side. I was expecting some blocks and something to represent any OCaml value. Is that possible? Or?
So there are actually those. There are types of general blocks used underneath, and yes. So there's an API. There's a low-level API built just on blocks, and that will have safety for lifetimes, but not safety for layouts, because you need to know when you're accessing a field, whether it's a pointer or not. So the higher-level API presented there is built on top of that API and has safety for layouts as well, so it keeps track of whether something is a record or a string.
But then if I define a type on the OCaml side, can I inject the value?
I have not implemented like general reflection of types into Rust yet, so you would have to use the low-level block API for those. I would like to just like be able to translate those a bit better. That's future work at the moment.
But then I can. Okay.
Next, yes. Yeah.
Okay. So the reason your C code goes wrong is that you are keeping references to OCaml values that the garbage layer doesn't know about.
Yeah.
So you can fix that statically in Rust, but if you use something like C++, you can do the safety dynamically using copy constructors and such things. So has anyone tried that? Because C++ has been around for a lot longer than Rust has.
I can speak to that. So, we do a lot like that, like So I mean, we have the exact same problem. We really need to basically aim everything has to be enabled with function. And we implement C++ and we use all sorts of template magic, smart modules, all that stuff, right? And simplicity that's also problems. So it doesn't actually for cases like this. So we have a separate tool called GCML that runs over the whole syntax tree. It's a static analysis that checks that you actually use this thing, right? And of course that fails when you code this inside a template because then it doesn't understand what's going on. So we have all the same functions that we iterations on these smart modules. So I'm actually quite excited.
Let's have Alan as the last question. He has his name on the last slide, so he gets to ask.
Yeah, so my experience with Josephine was that because you're wanting to maintain this invariant anytime you get a shared access to a GC contact object, you're wanting to make sure the GC doesn't run all that. And funnily enough, that's not actually documented in the SpiderMonkey API. So the way that I found that out was going and talking to people who wrote SpiderMonkey and asking them, are you ever likely to run GC during this time? So I was wondering if you had the same experience. How did you actually get the guarantees about when garbage collection runs?
Yes, so I've been actually working on the OCaml garbage collector for a while, so I have a decent knowledge at this stage of it when it doesn't. But also the OCaml manual in the interfacing with C section is actually quite precise and will explain all of these invariants. It's very difficult to actually manage to follow them all correctly when writing the C code yourself, but they are at least written down.
So I think we're out of time for questions. You will have to take this one offline. Could you please, if there is an empty seat next to you, contact and leave more space, then this one will be like mine.